We are thinking about friction in this video. So just imagine this situation. I'm pushing a crate across the floor. We've seen that kind of thing before. And so the forces on the crate are, of course, its weight. And then there's a normal force from the floor pushing up. That'll be significant in a minute. And another normal force from my hands, pushing forward. And since the crate is sliding across the floor, when surfaces slide across each other, there is kinetic friction. And it always points backwards, opposite to the direction of motion. Now, the friction forces have some similarities. That of course, they all come from the surface that the moving thing is sliding over. So of course in this case the friction force comes from the floor, and all the friction forces are related to the normal force that comes from that same surface. In this case that surface is the floor, right? Not this normal force, but this normal force. And they're related in very similar ways. Kinetic friction is just directly proportional to the strength of that normal force. And this factor here is called the coefficient of kinetic friction. And what it means is that it's a way of measuring how sticky the two surfaces are, how much they stick to each other. A bigger value for this coefficient, of course, gives you a stronger friction force, right? Because the surfaces are stickier or they're just more difficult to slide. Rolling friction works exactly the same way. It's proportional to the normal force that comes from the surface our object is rolling over. And again, this constant here is the coefficient of rolling friction, and it tells how well the rolling object sticks to the surface and rolls rather than slips or slides. The static friction force is a little bit different. You see here, it's still related to the normal force, and it's got a coefficient of friction, but it takes on a whole range of values. It could be anything from 0 up to this value. This is the maximum value for the static friction force. What's really going on there, something like this. Imagine I'm pushing this crate and I push just a little bit, but it's stuck. I'm not pushing hard enough to move it. It stays stuck. I'm pushing forward. I'm applying a forward pushing normal force, but it's still not accelerating in that direction. It's staying put, maintaining a constant velocity of 0, so it's got no acceleration, no net force. No net force means there must be some backwards force that cancels out my forward push. That's what the static friction force does. It keeps the crate from moving even though I'm pushing. And then if I push a little harder, it still stays stuck. And push a little harder still, it still stays stuck because the static friction force that is resisting my push is able to adjust up to a certain point. And it can, even if I push harder, it can match. It's still able to get bigger itself and continue to match my force and continue to cancel it out, continue to be just as strong as my force. That's what we mean by this range of values. I push a little bit stronger, and the actual value of the static friction force gets a little bit bigger, as much as it needs in order to continue to cancel out my push and keep the crate stuck. But of course, eventually I can push hard enough to get the thing moving, which means there's some maximum value of the static friction force, and if if I push with a force that's bigger than the maximum static friction, then I've got stronger force this way, and the static friction force in the opposite direction is weaker. So then there's now a net force in this direction, and it starts to pick up velocity in that direction. It finally starts to move. So that's how static friction works. But let's say right now I'm just, I already got this thing moving, and let's say it's accelerating just a little bit. So the crate's acceleration is 1/2 meter per second per second. And the mass of the crate will be 50 kilograms. And let's see, what else do we know here? Yeah, that's all we need to know in order to figure out what this number actually is for this situation, what the coefficient of friction actually is, or to put it another way, how sticky, how much does the bottom of the crate stick to the floor? Well, the procedure is always to start by identifying the forces that you've got. We've done that, and then take that information to see how those forces combine to give you a net force. In this case, the acceleration is this way, so the net force is in that direction. Newton's second law tells us net force points the same way as the acceleration that it caused. And let's imagine a coordinate system here where to the right is the positive x direction and up is the positive y direction. So we can think about the two components, the x component and the y component of the acceleration. The x component of the acceleration is all we've got for the acceleration. So x component of acceleration is just plus 0.5 meters per second. Since that's the only acceleration we've got, we have no acceleration in the vertical direction, so the y component of acceleration is just plain 0. Now, remember Newton's second law. One vector equal to another vector. If those vectors are to be equal, the x component of this vector has to equal the x component of this vector, and the y component of this vector has to equal the y component of this vector. In other words, x component of the acceleration is just 1 over mass times x component of the net force. And similarly, y component of the acceleration is one over mass times y component of the net force. But of course, there is no y component to the acceleration. This is 0, so the y component of the net force is going to be 0. That's actually useful information in a minute. So we think about the net force, and we think about how all these forces combine to give us net force. The best way to think about it when you've got forces in different directions is think about how all the forces that either point along the x-axis or at least have a component along the x-axis, how they combine to give you the net force in the x direction, and then how all the vertical forces, or forces that have vertical components at least, how they combine to give you the net force in the y direction. So let's do that. All right. Net force in the x direction, there's an easy way to write that down, to write down the algebraic expression that shows how the forces combine. All you have to do is remember, add all the forces in the positive direction and subtract all the forces in the negative direction. So in this case, in the positive direction, you've got the normal force of my push, normal force from my hands, minus, because it's in the opposite direction, it's in the negative x direction to the left, kinetic friction. And being a net force, it's equal to mass times acceleration. And since this is just the net force this is just the x component of the net force, it has to be equal to mass times the x component of the acceleration. Okay. This is all stuff that you've read in the text. If it seems unfamiliar, go back and take a look at it again. After this, if it didn't make much sense the first time, it'll make a little bit more this time. Okay, now do the same for the y direction. The y component of the net force is just all the force in the positive direction. That's just the normal force from the floor, minus all the force in the negative y direction. That's just the weight of the crate. And of course, being a net force, it's equal to mass times acceleration. Since it's the y component of the net force, it's going to be equal to mass times the y component of acceleration, which we already knew was 0. So as we've said already, the y component of net force is 0. This comes out to 0, which means normal and weight cancel each other out. So in this case, they have the same strength. In order to cancel each other out, they have to have the same strength. So normal force equals the weight, and we know how to calculate a weight if we know the mass of something. Weight is just mass times g. G is the usual 9.8, the acceleration due to gravity. Okay, now let's look at our problem again and see if we can figure out how strong that coefficient of kinetic friction is. This coefficient of kinetic friction actually appears in this term. So let's rewrite this this expression just a little bit. Normal force from my hands minus the kinetic friction, and kinetic friction is always coefficient of kinetic friction times the normal force that comes from that same surface. And that's equal to mass times acceleration. And since the acceleration is in the positive direction, one thing that tells us is that this force, the push from my hands, must be stronger than the backwards pushing kinetic friction. From thinking about the y dimension, we know that the normal force is just as strong as the weight, which is mass times g. So we can actually write that term as mass times g. Now we can insert the numbers and we can figure out what we have for a coefficient of friction. So in this case, what numbers did we know? We know the mass is 50 kilograms and the acceleration is 1/2 meter per second squared. And in this case, I didn't mention it earlier, but say we do know how hard I'm pushing. I'm pushing with let's say a force of 200 newtons. So put in all the numbers, and then you've got an equation that has only one unknown, coefficient of friction, and you can solve for that number. So it looks like this. Normal force from my hand is 200 newtons minus coefficient of kinetic friction times mass, 50 kilograms, times the acceleration from gravity, 9.8 meters per second, equals mass of 50 kilograms times acceleration of 1/2 meter per second. So 200 minus coefficient of friction, you add these two things together, it'll come out to 400, or you multiply those two things together, you get 490. 490 what? 490 newtons, because a mass times acceleration is a force. That's what Newton's law tells us. And if you always have the masses in kilograms, and you always have the distances in meters, and you always have the time in seconds, then multiplying mass times acceleration automatically gives you a force in newtons. Now, newtons will be the usual unit for quantifying the amount of force. That's the left-hand side, and the right-hand side is just 50 times 1/2, that's 25. 25 what? Again, mass in kilograms times an acceleration in meters per second. That gives us mass times acceleration means a force, and we've got all the right units to give us a force in newtons. Well, let's rewrite this equation in a slightly simpler way. That I subtract 25 from both sides of the equation, and after you subtract 25, remember this was 200 newtons, and I've got 175 newtons, and then let's add coefficient times 490 to both sides. So adding plus coefficient times 490 to minus coefficient times 490, that gives us 0. And then add plus coefficient times 490. Newtons. And then now it's easy to see how to get the coefficient. Just divide both sides by 490 newtons, and then our answer looks like this. One 175 newtons, and then divide both sides of the equation by 490 newtons. equals the coefficient of kinetic friction, and that comes out to, let's see, about 0.36. And since you've got newtons in the numerator, newtons in the denominator, and you can treat unit labels as if they were algebraic variables, these two unit labels cancel each other out, and a coefficient of friction will have actually no unit labels. It's just a plain number. Okay, now let's look at a slightly different situation. Same crate, but now it's sitting still, and I'm trying to get it started moving. And I push on it a little bit, and it doesn't move because static friction is strong enough to cancel out my push. I push a little harder, and it still doesn't move because kinetic friction can still adjust and be strong enough to cancel out my stronger push. But I get to the point where I finally push hard enough that static friction cannot match my push, and then the crate starts to accelerate. So what's going on in that case? Let's say I'm just at the point, just on the verge of getting that crate moving. So at that point, a point at which I just push it, if I push a tiny bit harder, I will at that point be pushing harder than the maximum static friction. So static friction will not be able to counteract my push any longer. It can't get big enough to counteract my push any longer, and then the crate starts accelerating. So the normal force from my hand and the weight and the normal force from the floor, they're still there, and static friction. Now I push just a tiny bit harder, say 270 newtons. Just a tiny bit more than 270 newtons is enough to overcome static friction. It's enough to defeat the static friction and get the crate moving. So that must mean that the maximum possible value for static friction is 270 newtons, because if I push harder than that, static friction can't get big enough to cancel out my push and keep the crate stuck. And maximum value of static friction, as I pointed out a minute ago, is related to this normal force again. It's equal to a coefficient of static friction. That's going to be a different number from kinetic friction times the normal force. Now, it's still the case that vertically there's no acceleration. When the crate changes its velocity, it gains only horizontal velocity. It accelerates only in the x direction. So there is never any y acceleration, which means there is no net force in the y direction. Or the y component of net force is still 0, which means that these two forces still cancel each other out, which means they have the same strength. They can't cancel unless they have the same strength. So the normal force is still equal to the weight, and in the previous question we figured out what that weight was. 50 kilograms times g, and that came out to 490 newtons. 490 newtons. And so the normal force is equal to 490 newtons because we know these two forces must be equally strong since there is no net force along the vertical dimension. Vertical component of net force is 0. Okay, so now we have an equation where, now that we know this number, this is the only unknown, and we can solve for the static friction force, and that will look like this. $270 newtons divided by 490 newtons equals the coefficient of static friction. And then 270 divided by 490, what does that come out to? Comes out to about 0.55. And notice that coefficient of static friction is a little bit bigger than the coefficient of kinetic friction. That's just about always the way things work. Static friction is a tougher kind of friction, a stronger kind of friction than kinetic friction. And then also it turns out that rolling friction is the weakest type of friction. It will have coefficients of friction smaller than what you'd get for static friction or kinetic friction. Look at one last question here. One last question. Imagine that you're in a curling tournament. So you slide the curling stone down the ice and try to get it to stop in just the right place. And the surface of that ice is very, very smooth, which means the kinetic friction force that the curling stone feels is tiny, but not exactly 0, because eventually the stone does slow down to a stop. So just draw, say, a motion diagram for the curling stone. Sort of like that. And we will say that at the end of the 4th time interval, however long those time intervals are, it has come to a stop. That's the moment when the final moment when we're interested in things. So that's the final velocity, which is 0. And the initial velocity it has here, as soon as it leaves the hand of the pusher, is, let's say, 1 meter per second. And from that, that's enough information to go back to our Chapter 2 kinematics stuff and figure out the acceleration. And then it turns out that once we know the acceleration, we can actually figure out the coefficient of friction for ice and the stone. So what do we know here? Let's set up our coordinate system so that this is the positive direction, and that the initial location where the stone first started moving after it left the hand of the pusher is right here, and we'll say that the initial location is 0. And the final location, right over here, 10 meters. So the stone travels 10 meters before coming to a stop, before slowing down from 1 to 0 meters per second. So we know the initial and final locations, 0 and 10 meters respectively. We know the initial and final velocities, we're trying to figure out the acceleration, so we don't know that yet. And we don't know how much time it took for the stone to travel those 10 meters and slow down to a stop. Acceleration is what we're trying to find. We don't know anything about time, so what we need is an equation that has acceleration in it but doesn't have time in it. If it did have time in it, we'd have to figure that out first before figuring out the acceleration. And we do have one equation that will give us the acceleration when we know distance traveled but not time, and it's this one. Final velocity squared equals initial velocity squared plus 2 times acceleration times the difference between final and initial location. And we can put in all the numbers here. Final velocity is 0. Initial velocity is 1, so initial velocity squared is also 1. 1 meter squared per second squared, since it's a squared velocity. And then plus 2, acceleration is what we're trying to find. Final location is 10 meters, initial location is 0. So this difference, final minus initial, is 10 meters. And then we can figure out what that acceleration actually is. Minus 1 meter squared per second squared equals, I just subtracted 1 meter squared per second squared from both sides of the equation, so it's gone from the right-hand side. All we have left on the right-hand side is acceleration times 10 times 2, so I'll just call it acceleration times 20 meters, and then divide both sides of the equation by 20 meters, and that gives us the acceleration. So the acceleration is minus 1 meters squared per second squared divided by 20 meters. So that's minus 1/20th, or 0.05 if you prefer, meters per second per second. Right? This unit of meters cancels out one of the units here, so we're left just with units of meters per second, just exactly what you should get for an acceleration. And now that we know the acceleration, we can use Newton's second law and use what we know about kinetic friction in order to see what the coefficient of kinetic friction is for the ice as the stone slides across it. What's happening in this situation is there are just 3 forces on the stone after the pusher has stopped pushing. Weight, which is, of course, mass times g, and then normal force from the surface of the ice pushing up, and then let's say it's moving left to right, and that's the positive direction as I decided when making the motion diagram. If it's slowing down, of course, the velocity and acceleration point in opposite directions. So if the velocity is this way, the acceleration has to be the other way, and Newton's second law tells us acceleration points the same way as net force. So the net force points this way. that means there has to be some kind of horizontal force. If there aren't any horizontal forces, you can't have a net force in the horizontal direction. And of course, the net force in this case is the kinetic, or the horizontal force is the kinetic friction. You've got something sliding over a surface, so there's kinetic friction, and kinetic friction is always opposite to the velocity. So the net force is entirely horizontal, which again means the vertical component of net force is again 0, which again means that these two forces have to cancel out. And so again, that means that the normal force is equal to the weight of the stone. Normal force equals weight equals m times g. All right. So then from this diagram we see that these two forces cancel out, and the only force that's left over is kinetic friction. Kinetic friction is the only force in the horizontal direction, so the horizontal component of the net force is simply caused by the kinetic friction force. I decided that the positive direction was this way and kinetic friction points the opposite way, so it points in the negative direction. So when I put it into the force equation, I have to put it in with a minus sign. And of course, kinetic friction is coefficient of friction times normal. And the normal force is, again, like in the previous two examples, weight, mass times g. So that's the net force. And the net force being the net force, it's equal to mass times acceleration. And we know what the acceleration is. So let's write out what I just said. That's the only contribution to the net force, so it is the net force. And being a net force, it's equal to mass times acceleration. And we just figured out what acceleration is, negative 1 over 20 meters per second per second. But notice that there's a factor of mass on both sides of the equation. So we can divide the whole equation by mass, and we don't even need to know what the actual mass of the curling stone is. That's convenient, because I never said what the mass was. And all we have then is minus coefficient of friction times g, 9.8, equals negative 1 over 20 meters per second per second. So then look, there's a minus sign on both sides of the equation, so you can divide the whole equation by minus 1, those minus signs disappear. Divide both sides of the equation by g, which is 9.8. And we're left with coefficient of friction equals minus 120 divided by G, which is 9.8. This is 1 over 20 meters per second, and then this is 1 over meters per second. So all the unit labels cancel out just as they should, and give us a coefficient of friction that has no units at all. That's the way the coefficient of friction is supposed to work. So what is that number finally in the end? Let me grab my calculator. Oh, sorry, minus signs canceled out. So we've got 1 divided by 20 divided by 9.8. And then the coefficient of friction then is 0.0051. A really, really small coefficient of friction, which is exactly what it's supposed to be because the stone is sliding on very, very smooth ice. All right, that's basically the idea how to think about friction forces. In the next video, we'll think a little bit about drag forces.